So we're ready to test all the candidates for absolute max and absolute min. I found the ones inside, so here are all the candidates inside of the region. There were these two were out off the mattress, right? So they don't count. That's why I crossed them out. But these two are within the confines of the mattress, and a saddle point won't be absolute max or absolute min, because in some direction it goes up from a saddle, in some direction it goes down from a saddle. Saddle points can't be an absolute max or min, but this local min might be absolute min. So we got this one that's inside, and then we have to check the boundary. So I did y equals 0, and I got 2 critical points on that boundary. And x equals 3, I got 1 critical point on 3, 2. And then at y equals 4, 1, 4, and negative 1, 4 critical points. And then at x equals negative 3, 1 more critical point. And then we're going to check all the corners. We're going to check all the corners too. So that makes 11 total things to check. Any questions about what's up there before I erase it? So you've got web work on this stuff. Several to do like this. Okay, so be careful. So after a while, I just saw that there were no terms here that had both x and y in them. So it didn't matter what I plugged in for y. I always got the same derivative with respect to x. If there's overlap, if there's terms that have x and y, you can't just do that, right? You've got to plug in the value, get the new c function, and then take the derivative. Does that make sense? So just because I'm putting in values of y doesn't mean you're going to get the same derivative with respect to x every time. The reason that happened here is because there's no terms that have both x's and y's. So that's why I kind of streamlined that. So be careful. Don't just assume you can do that at every problem. Are there any questions about? Yes, please. Yeah, so corner points will always be on the boundary, and there'll always be potentials that you'll have to check. Because they're endpoints of these, right? So when we're doing each of these problems, so we can do this problem, we got the critical points, and then we need the boundary. The boundary would be those 2 corners. So it's like the negative 3, 0, and the 3, 0 would be included in this up here. But instead of rewriting those all over and over again, I just wrote them once at the end. Yeah. Other questions? Yeah.
So then, once you have all the points, you plug them back into your original, and whichever.
What do we want to know? Yeah, we're trying to find the absolute max concentration and absolute min concentration. These are the locations that are candidates for those. So we're about to do that. Other questions before I take it all down? It's on the video. I got this recording. Okay, did someone have those 11? Okay, here we go. First one. Quick. Anyone? 1, 2. Next one.
Negative 1, 2.
Thank you. Negative 1, 2. Next one.
Negative 3, 0.
Negative 3, 0. 3, 0. 1, 2. I got that one already. 3, 4. Negative 3, 4.
1, 0.
1, 0 is 1. Negative 1, 0. 1, 2, 3, 4, 5, 6, 7, 8. 3 more.
3, 2.
3, 2. Negative 3, 2. Last one. I didn't get 1, 4 yet.
Yeah, because the negative 1, 2 was the saddle point, so it's not supposed to be.
Oh, okay. Negative 1, 4.
Yeah.
So which one is saddle?
That green one,
The second one.
This is saddle point, so we know it can't. It doesn't hurt to put it in there. It's just we know it won't be absolute max or min. So I can leave it and take it out. Okay. So the first question was, is there any place on the mattress that's free of bed bugs? Okay, so yeah, you get yourself in a real tight ball and you sleep right there. Okay, where? Negative 3, 2. Okay, and then where do we want to focus our exterminating efforts here? 3, 4. 3, 4 has the highest concentration. Okay, any questions about this problem? Yeah, Chris.
So if you're using determinate, like if
Discriminant?
discriminant,
Yep.
sorry, not
Mhm.
determinate.
Yep.
Like if you plug in 3, 4, you get a value greater than 0, but also the second partial derivative is greater than 0, which says it's a local.
It should have been local min.
So,
Which point?
at
3,
3, 4.
4.
Yeah, it's the maximum.
But it's not. But it wasn't. It's not a critical point. This is a boundary point, right? 3, 4.
Okay.
Yeah. So just because, so that only is true on the critical points. So this is somewhere on an upcline or a downcline or something at the boundary. So the discriminant doesn't apply. Other questions? Okay, take a look at the sheet. We're gonna move on to the next chapter. So different topic here. What's that?
For the D, like this is the discriminant F, or it would be CXX, and then times CYY,
Right.
which is negative anyway. It's 3, 4.
Oh, he's saying it's negative. It doesn't matter. It doesn't apply to a non-critical point. So, okay. So here's a function, and this is a rate of change function. A multivariable, two-variable rate of change function. Okay, so it represents the rate of change of snow fallen with respect to both time, that's one of your independent variables, and elevation on a mountain. Okay, so the output value has units, volume per hour per 1,000 feet. So 1,000 feet of elevation distance. Okay, and so here's the contour plot that gives us, that's the contour plots for the function capital S. So using the contour plot, interpret the situation. So you got 2 warm-up questions, A and B. Let's do those. Just do those. So think about that and then talk to the person next to you. So it's just what we understand what's going on here. Anybody else need a sheet? Handout. Okay, so at 3,500 feet, 1.4 hours, what's the situation there? I heard 0.4. All right, so 0.4 what? So the contour plot tells us that it's 0.4. So the units is volume per hour per 1,000 feet. All right, so this is a little weird, but how would we interpret that number? What's the meaning of that? That's a rate of change, but it's kind of like a double rate of change, right? It's a rate of change with respect to 2 variables. At the same time, how would we interpret that number? Yeah, Griffin, go for it.
So, at the instance of, this is 1.4 hours, and at the elevation of 3,500 feet,
Uh-huh.
the snow's changing of 0.4 volume, whatever the unit is.
Uh-huh.
So that at that instant, at that elevation of time, that's how much the snow is changing by.
Okay, the volume is changing by.
Yeah.
And how do we interpret rate of change values? That's true.
For every little bit of change.
Okay, so
In each of those variables, that this volume of snow changes 0.4 times as much.
Okay, this is a little more complicated. We either have to pick a change in one of the variables or both. So if we pick a change in, say, hours, if we pick a change in hours, then so given a change in time, we'd say the change in something is 0.4 times the change in time. The change in what? The change in what is 0.4 times the change in time? Volume?
Volume per hour.
Volume per 1,000 feet. So it's really the change in a rate. It's a change in the other rate, right? So given a change in time, the change in the rate of change, like the partial rate of change of volume with respect to elevation would be 0.4 times that change in time. We're entering the twilight zone. Okay, so does that make sense? Right, so given a change in time, 0.4 times that change in time would give us the change in, the small change in the rate, the partial rate of volume with respect to elevation. Okay, what if we took both a small, so maybe more would be easy, and we could do it the other way, right? We take just a change in elevation and we come up with the change in the other partial derivative. But maybe what makes the most sense is to take a change in both. Take a little change in time and a little change in elevation. Do I have a variable for that? Capital E, so actually it's capital T. Capital T, capital E. I'm going to take a little change in both. And if I take a little change in both, it would determine what? The change in volume, right? The change in volume, right? So given a little change in both, both time and elevation, the change in volume would be 0.4 times, right? The change in elevation would be 0.4 times the product of those changes. So maybe that's maybe easier to grasp. Okay, so now let's talk about these other questions. Questions on that, interpreting the value 0.4. What was the other one? What is the rate of change at 1.8 hours and 5,000 feet? Just to make sure we read the contour plot right. 1.6? Rate of change, 1.6 volume per hour per 1,000 feet. And we could do the same kind of interpretation there. Okay, so don't lose sight of that. It's going to be important. So now we have a little bit of volume is 0.4 times dT. Now that's only true right around 3,500 feet in 1.4 hours, right? As soon as you change elevation, change time, the snow's been falling, we get a different multiplier, right? We get a different multiplier because the rate is a continuous function depending on the values of the two independent variables. Okay, so this is only true close to this ordered pair of independent values. Okay, let's try this now. So suppose that our goal was to figure out the total volume of snow fallen at all elevations over the time, over the 2-hour time frame. Say from 0 to 6,000 feet, from 0 to 2. We want to figure out the total accumulation of snow fallen. So here's one step in doing that. One step in doing that would be, look at numbers 1 and 2. Can you read that in the back? Make it a little bigger? Too big. That's the best I can do. Oh no, I can do a little better. Hold on. There we go. Okay, so estimate we want to look at the first 0.4 hours between 3,000 and 4,000 feet. So let's just isolate a little bit of this contour plot. and see if we can find the accumulation of snow just in there. And how would we do that? Well, we need to pick a constant rate for that region of interval time and elevation time. With a constant rate, then we can use that thing like we just found, right? So in the first 0.4 hours between 3,000 and 4,000 feet, can you come up with a ballpark? What's a constant rate of change that would be something like a best match to what the actual rate of change was, the changing rate, right? So what are we doing here? So between 0.4, 0 to 0.4, and 3,000, 4,000 feet. So we're talking about 0 to 0.4, blue, and 3,000 to 4,000 feet. So we're talking about right here. So if we just want to get a quick and dirty estimate of how much snow fell in that time frame, in that elevation frame, what would we need? We need a constant rate, right? We need a constant rate. So what do you think? This is 0.2, just down here is about 0.2. This is what? This line is 0.4. 0.6 is up here. So what single rate might we say? So if 0.4 came right through the middle like this, then we might say 0.4 for the whole thing, right? So because 0.4 does this, is it going to be less or greater than 0.4, our estimate? Less, because there's more area here below the 0.4 than there is above the 0.4. So maybe 0.35. Not 0.3, because that would be like if the 0.4 was up here, all the way up here. So I think that's a pretty decent estimate. If we want to just throw one rate at this whole chunk for this changing rate, 0.35. Okay, so if the rate of change was constant in that time frame and that elevation range, what would the total volume of snow be? Go. What would the total volume of snow be? So I should have probably called this R sub S. That would have been better. So if I wrote this some time back. So the R sub S would have been a better name for this. So what's the R sub S that we're estimating here? We said 0.35. So the little amount of volume here for that. Yeah, what happened? So it's like we're on the mountain, right? we got a cold breeze in here. All right, so dV equals what? How'd you get it? 0.35 times dt is 0.4. Elevation 1,000, but this is per 1,000, right? So we would be 1, right? Because this 0.35 is per 1,000. So what do we get? 0.14 somethings of snow. Well, okay, but what is the units on this 0.14? It's just units cubed. It's volume. Whatever this unit is. So yeah, so it's not meters cubed and it's not kilometers cubed, right? So okay, so how would we get the exact amount of snow fallen using this changing rate of change then? So what would the idea be? Yeah.
Can you go over how you got that estimate for 0.25 again?
Well, I just was looking. Like I just assumed this is 0.2 along here. This is 0.4. And then 0.6 is up here somewhere. This is just ballparking, right? So if the 0.4 went right through the middle, then I would call it 0.4. But the 0.4 is up higher. That means there's more lower rate than higher rate. So I just made it a little bit lower than 0.4. Is it better? Okay. All right, now we want to find the exact amount of snowfall, and according to this changing rate in this time frame and in this. Yeah.
Would you integrate the rate of change of the?
Okay, so we're going to integrate the rate of change. Is it?
We'll need to integrate along T and the elevation, so it probably end up being double integral.
Right. So this is so we're accumulating both. We're accumulating snow both as time goes from 0 to 0.4 and as elevation goes from 3 to 4. So we could say we could accumulate from 0 to 0.4 first, but what would we be accumulating? We'd be accumulating kind of like the rate, right? Like the rate of change of snow with respect to elevation. And then when we accumulate that, we get the amount of snow. Yeah.
Why did you pick 0.4 and not 0.2?
We're still on the constant rate.
Well, okay, then why?
All right, so here's 0.2. 0.2 came along here, kind of the bottom, and then I just said kind of 0.6 is kind of up here. And then if 0.4 went through the middle, then we would just say 0.4. What?
Yeah, 0.4 is a change in hours.
You're talking about this here?
That's the time.
dV equals, so this is the change, dt and dE.
More generally, how do you
It was said-
It was given. It was given. Here,
okay, then how did you get
it's given from 3 to 4,000 feet. It's this box, right? We're looking at this box right here. We want to know the volume of snow according to this box that was given in the problem.
Why is it DE of 1,000?
Because this is in thousands of feet. This unit is per 1,000 feet. It's not per foot. If it was per foot, I'd put 1,000 here. But this unit is in per 1,000 feet. So I'm going to put per 1,000 feet for my DE. The units have to match up. You're not convinced. This unit is per 1,000 feet. It's not per foot. If it were per foot, then I'd put feet over here.
I just don't understand how you
Choose what?
Oh, good.
So yeah, so this is the rate of change per hour and per foot. Adam, you need to teach the class. Okay. So where were we? We were talking about getting the exact amount of snow for this thing. So what we could integrate the exact rate of change function. So I want to change the name to R sub S. I like that better. And I first want to integrate that from 0 to 0.4 with respect to dt. Okay, and what did we say? We said if you do that, well, this is kind of like the change in the rate, right? It's like the change, and it's accumulating changes in the rate of volume with respect to elevation. So now if we want to get total volume, we'd have to do what? We'd have to integrate that from 3 to 4 with respect to, I can see, haste makes waste. Okay. So what would this do? This is gonna okay, or you can think of this as we're going to integrate from 3 to 4 dt. So this whole thing is the rate times dt times dt times de. As we saw, is a little bit of volume, right? And we're gonna have to accumulate all that volume over this region from 0 to 0.4 in time and from 3 to 4 in elevation. So you can think of it as a two-step process, or you can just think of it as accumulating all the dVs in 2 dimensions. So either way, two-step process, the way I wrote it here with the parentheses. Accumulate up and get what? Like the changes in the other rate, right? So it's like accumulating up the changes in the other rate, and then integrate with respect to that variable. Or just think of this whole thing as dV, and we're accumulating all the dV over that region, 0 to 0.4, 3 to 4. So this is, we're entering the idea of double integral, because that's when you have multivariable functions, and you want to accumulate. When there's two independent variables, you don't have a single integral, you get double integrals. So that would be the exact amount of snow that we approximated to be what, the 0.14? What was it? 0.15? 0.14. So 0.14 was our approximate by picking off a constant rate for the whole thing, and then that would represent the exact amount of snow fallen over that time, over that elevation change. Any questions? Yes, sir? What's that? So, okay, no, so in this case, no. In this case, no, because we've got like a rectangular region. With a rectangular region, you can do it either order. So we could have done, yes, we could have done elevation first, and then we've been accumulating changes in the rate with respect to time, and then the time integral. So yeah, with a rectangular region, it's interchangeable. We'll get that later. That's next, after break. Okay, questions? All right, so you'll have for next